Let's see. Data link layer devices. Starting at the top, repeaters. We talked about these before. Basically, all it's doing is it's copying information that was already sent and then resending it at an amplified signal level. I used the example of IDSL during the last class, and that's a perfect example again. You know, IDSL, you've got to have multiple repeaters on the line because of the physical distance that the signal's traversing compared to the technology type and how far that signal can generally traverse. You've got to have multiple, one or more repeaters a lot of time on IDSL, most of the time two repeaters, to make sure that that signal gets from one end in the CO all the way to the customer's end. And then a hub is basically a multi-port repeater. You guys definitely need to know the difference between a hub and a switch. Like a hub is just a really dumb device where everything connects there like it does for a switch. You've got all these various Ethernet cables plugging into a hub like you do for a switch. But unlike a switch, the hub does not segment any of that traffic out or decide like which port it needs to go to. If one, you got 10 devices on there, one device sends some information, it's going to go out to all 10 devices that connected to there. So hubs are not really seen all that frequently. Like a few years ago, you could still see them just because they were cheaper, but the cost of switches have come down on like cheaper switches, and so like you really don't see hubs at all. They're really cheap, kind of dumb devices that just send all the information out at every port. And then a bridge and a switch are very, very similar. A bridge separates collision domains, as does a bridge separates collision domains, as does a switch. A hub obviously does not. You've got all the data colliding at one time. So that's another thing with hubs is, in addition to like a lot of data being sent out to every single port that doesn't need to be, if you get too many devices on a hub, frequently you wouldn't be able to communicate at all. Because if you've got 10 devices, they're all sending data, and a lot of times you won't get a lot of collisions because, hopefully that many devices won't all be sending at one time. But if you've got a hub with 100 devices plugged into it and they're all trying to communicate, you're probably not going to pass any traffic at all because they're constantly going to be colliding. The packets are constantly going to be colliding with each other. So a bridge separates the collision domains so that you don't have that problem anymore. The other difference between so a bridge usually just separates two collision domains. A switch actually has lots of collision domains, one for each port. So that's kind of the difference between a bridge and a switch. The other difference is the way that it analyzes and forwards frames. A bridge uses software to analyze and forward those frames, whereas the switch is hardware-based. It uses those ASIC, application-specific integrated circuit chips to analyze and forward frames, and so it's actually a lot more efficient than a bridge because it's got a specific piece of hardware that's handling that each time. And the other thing is because you've got each port separated into a collision domain, you also have a dedicated amount of bandwidth for every port on a switch. And this is kind of a visual example. We just talked about a bridge. Each of these right here represent hubs with a couple computers connected to it. The bridge is right here. So these two computers are both in a collision domain. Like if they both try to send traffic at the exact same time, the CCNA CD carrier sense multiple access collision detection algorithm will come into play. It'll realize that there's been a collision, and each of those computers actually each port on the hub will tell the computers that they can't pass traffic for a random amount of time based on this very specific algorithm, and they'll have to count down. So you'll have a lot of times where they're not able to pass traffic, especially if you have a lot of devices connected on those hubs. So because the bridge can separate those collision domains, you don't have that problem. You don't have to worry about sharing bandwidth, at least on the bridge level.
Does the bridge only send information to the relevant collision domain?
Correct. Correct. Since you're separating those collision domains, it's not gonna just forward it out every port like a stupid hub would. And then a switch is, just as we described a minute ago, is the same thing as a bridge, but it's a multi-port bridge. So instead of being able to just break it up into two collision domains, you got a separate collision domain for each one of those. So each of these individual PCs is in its own collision domain. And then half duplex and full duplex. really it's just whether it's able to send and receive traffic at one time or at the same time. So half duplex is one-way communication. You can only send or receive one at a time, not both. Bandwidth can suffer a little bit due to, as we talked about before, on the hubs, the CSMA CD. And then full duplex is, just double that. You can do two-way communication at one time, or send and receive simultaneously. And that's actually the end of the high points on Chapter 3. There's a lot more detail that I didn't go into on the various cabling standards. And like I said, I would read over that, but I wouldn't place too much effort on trying to memorize every single little cabling standard in there. You're already going to have a lot to memorize, especially what we went over in the first two chapters as far as the OSI model and that kind of thing. So definitely read over. You should be familiar with, have read over the cabling standards, but I wouldn't spend a whole lot of time memorizing more than the way that they're named and why they're named that, like we just covered. Does anybody have any other questions on Chapter 3? Preferably one I can answer, unlike David's question.
I looked it up and it just says E was for enhanced, and it's 1,000 megabits, and it had a lower frequency.
Okay.
It can handle maybe it's a higher frequency, but it didn't say that it was any other.
Okay, I wasn't sure if it was enhanced or extended, but I guess if it's 10 base, whatever the last part of it is going to dictate the distance anyway. So
it says it replaced all new installations are all 5E. Never uses 5E.
Okay. That clarifies that. Yes, sir.
Examples of the unicast, multicast, and
what do you mean, Well, there's two ways of doing those, because there's unicast, multicast, and broadcast at the layer 2, the MAC layer, and then you also have unicast, multicast, and broadcast at the IP layer. And I could probably give you actually a lot more specific answers on the IP layer. On the IP layer, multicast specifically, if you guys ever tune into streaming audio or streaming video, yeah, not here anymore. Streaming audio or streaming video, online radio, all those guys are going to be using multicast IP, because you can't. There's no way they're going to have the bandwidth to just be able to forward that specifically out to a million different users. So they've got certain ranges of IP that, just like there was a certain broadcast range, certain ranges of IP that are dedicated for multicast. So they'll get one IP like that, and if their network's properly set up for multicast, you just forward it out to that IP, and it goes out to each of the individual. I mean, it's still going to end up getting segmented out once you get into the greater internet. It's still going to have to go to the individual users, but at least from that individual, streamer's bandwidth, they're not going to have to dedicate everything for every single user, just a single stream. And then a broadcast you might get where you're sending it out to everybody. You're trying to find a specific IP. You don't know where it's at. So you'd send out a broadcast to all the nodes on the network, saying, hey, I'm trying to find this IP in this specific VLAN subnet range. And then you'd either not get a response because that IP is not in use, or you'd get a response from the device that's on there. But everyone would hear the broadcast message.
So for the data link layer, as far as the unicast and multicast, does that have anything to do with ARC requests? Or is that?
You'll actually.
What's the MAC addresses are involved?
Right. You'll actually send out a multicast or actually a broadcast frame to get from the switch or whatever to get the ARPs of all the individual devices. Of course, that on a layer 2 level, that information is also sent on a layer 3 broadcast. So you'll get back the layer 2 information attached to that.
Okay, so it's not just specific to layer 2 then. It's included in layer 3.
Right. All right, so anything else on data link networking before we jump into the next round?